Okay, this is our second example of a Faraday's law calculation. Now in this situation, we've got a coil, but it's not a single loop of wire. We've got a coil that is actually going around and around and around multiple times. In fact, there are, in total, 200 turns of wire. So a loop has 200 turns. The area of our loop is equal to 0.04 meters squared. Now in an exam problem, they could very easily give you the length and width dimension and you could calculate the area. That shouldn't be a problem, but for the sake of expediency, I'm giving you the area because I'm assuming you all know how to work out the area of a rectangle. So there's the area of the loop. Now the other dimension of this problem, which is different to the last problem, is this. I'm not giving you the time that it takes to go from one position to another. What I'm telling you is the frequency of rotation. In other words, this coil is spinning around and around and around with a frequency of 50 Hertz. So it completes one full rotation. I'll try that again. It completes 50 full rotations in 1 second. So that means, of course, that it completes 50 rotations in 1 second. The magnetic field strength is we'll make that 2 Tesla this time. So there's our magnetic field lines. Magnetic field strength is 2 Tesla. Now, the question is this. What is the average voltage generated in the ends of our coil across there and there? That's where we're going to measure the voltage. What's the average voltage generated in this coil as it moves from this position to the vertical position? So it's going from a horizontal orientation, so it's going from this arrangement, a horizontal arrangement, to a vertical arrangement. Now obviously it's spinning and spinning and spinning, but we're going to take 2 quick instances from when it's there to when it rotates to its vertical orientation. During that short instant of time, what was the average EMF being induced in this coil? So let's go ahead and work it out, and I'll show you how this is done. This is just a little bit of an extension on top of the previous problem. So once again, we're going to use Faraday's law, and I'm going to ignore the negative sign for the purposes of calculation because we don't need the negative sign just yet. So the EMF is going to equal, now we've said before, it's the rate of change of flux. But that applied to one single turn of wire. If there's more than one turn, we need to multiply that value by the number of turns. So it's going to be n times the rate of change of flux. And so what we will get is this will actually increase the amount of voltage we're actually generating. So that's why generators have hundreds or thousands of coils on them, not one, because it actually increases the EMF or the voltage being produced. So let's go ahead and work this out. Well, once again, we use two key positions. We use the position when the coil is horizontal, and when the coil is horizontal, because none of the field lines can pass through the coil when it's horizontal, then we know the flux is zero at that instant. And when the coil is vertical, that's when the maximum amount of flux can flow through. So our change in flux, remember, equals the final minus the initial. And so that will be the maximum and the minimum flux. So in this case, we need to know what the flux is when it's at a minimum. Well, we know that it's zero. So the minimum flux will be zero because no field lines can pass through it. When it's a maximum, the maximum flux will be B times A. And that will equal, that's when it's in the vertical orientation. And that will be the magnetic field strength 2 multiplied by the area of the coil, which is 0.04. And that will equal 0.08 Webers. So every quarter of a turn, it's going from zero flux to 0.08 Webers of flux. So when the coil is horizontal, there'll be zero flux. Then when it's vertical, the flux through the coil will be 0.08. When it's rotated to that position again, it'll be zero again. Then it'll be 0.08 and so on. Okay? So we're looking at these two key instances. So that's when the minimum flux will occur. Minimum flux, and this will be the maximum flux. So the change in flux will be the minimum minus the maximum, which is 0.08 Webers. So we now know that the EMF is going to equal 200 times the change in flux, which is going to be 0.08 Webers, divided by the time taken. Well, what's the time taken? All we know is the frequency. But hang on, we also know that the period equals 1 over frequency. So 1 over 50 is the period, which is 0.02. So that's the amount of time it takes to complete one rotation, 0.02 seconds. But we're only interested in quarter of a rotation, from there to there. So we want a quarter of that. So the actual time will be 1/4 of 0.02, which will be 0.005, I beg your pardon. So now we have all the information we need to calculate the average EMF between that horizontal position and the vertical position. And the answer will be 200 multiplied by 0.08 divided by 0.005. And that answer is 3,200 volts. So the voltage we're going to produce is 3,200 volts. So there's our second example of Faraday's law.